Hello everyone, welcome back to the channel. Hope you all are doing well. So in this video we'll be solving another problem from LeetCode, and the name of the problem is course schedule. It is one of the very important problems based on an important concept. So according to the problem statement, we'll be given some number of courses, let's say n, that we have to take, labeled from 0 to total number of courses minus 1. Along with this, we'll be given an array prerequisites where at each index we'll be given a pair ai comma bi, which indicates that in order to complete course ai we first have to complete course bi. For example, if we are having a pair 0 comma 1, then it means that in order to take course 0 we need to complete course 1 first, right? We are asked to determine whether we can finish all the courses or not. If we can finish, we need to return true. If we cannot finish all the courses, then we have to return false. So this was all the problem statement. Now let us understand the approach to solve this interesting problem. Alright, so this problem is basically based on an interesting concept of topological sorting. So what is topological sorting? Let us first understand it. So topological sorting basically means that the linear ordering of vertices such that if there is an edge from node u directed towards node v, then u appears before v in that ordering. So we can understand it this way, that if node v is dependent on node u, then we make a directed edge from node u towards node v, and then in our topological sorting we want node u to appear before node v, because node v is dependent on node u, and that's why in order to reach node v we first need to reach node u. So this is how we can understand it. So now let us take an example to understand topological sorting better. Let's say this is an acyclic directed graph that we are having. We need to determine a relevant ordering after performing topological sort on these vertices. Okay, so what we are going to do is, if there is a directed edge from node u towards node v, so we are going to write them down here. We have an edge from node with value 4 towards node with value 0, so 4 will be our u and 0 will be our v. Okay, similarly we have an edge from node 5 directed towards node 0, so again 5 will be our u and 0 will be our v. We have a directed edge from node 4 towards node with value 2, so we can say that this, in order to reach node 2 we need to complete node 4, we need to reach node 4 first. So 4 is our u and 2 is our v. Similarly here also we have a directed edge from node 5 to node 1, so 5 will be our u and 1 will be our v. Then we have an edge from node 2 to node 3, so 2 will be our u and 3 will be our v, and the last edge that we are having is from node 3 to node 1, so 3 will be our u and 1 will be our v. So as you can see, we are having 6 vertices and we have mentioned all the directed edges here. Now we need to determine the topological sorted ordering of these vertices. So as I told you before, how topological sorting works is that if we have an edge directed from node u towards node v, then in our topological sorted ordering we want node u to appear before v in that ordering. So here also we can consider that if we have an edge from node u towards node v, then v is dependent on node u. Okay, all the nodes which are on the right hand side under v are the nodes which are dependent on other nodes. Okay, so how we are going to begin? We are going to check which is the node that is not dependent on any other node. So the vertex that is not labeled under v is the node that we should start with. On checking, as you can see, vertices 4 and 5 are not present here. It means that they are not dependent on any other node, and hence we can begin with them. Okay, so in our topological sorting we can first write 4 and 5. After this, again we are going to check the right hand side, and now we are going to find which is the other node that we can now reach after reaching nodes 4 and 5. On checking, as you can see, node 2 is only dependent on node 4, as we are already done with node 4. So the next vertex that we can write can be node 2. Okay, now again we are going to repeat the same process. We will again check our right hand side and see which is another vertex that now we can perform. So we cannot perform, or we cannot reach vertex 1, because even though we are done with vertex 5, vertex 1 is also dependent on vertex 3, and we are not done with vertex 3 yet. But here, as you can see, vertex 3 is dependent on vertex 2, and as we have already reached vertex 2, it means that in our ordering the next node that we can have is vertex 3. Now we are done with node 3 as well, which means that the next node that we can have in our ordering can be node 1. So here we can write node 1. Last node that we are left with is node 0. Node 0 was dependent on node 4 and node 5, and we were done with them in the beginning only. So now we can write node 0. So this is one valid topological sort ordering of this graph. Now there can be other valid orderings. Okay, there is an important point about topological sorting that you must remember. So topological sort is possible only for directed acyclic graphs. So let us consider this directed cyclic graph. Now we have an edge directed from node 1 to node 2, and we have a directed edge from node 2 to node 1. It means that in order to complete node 2, we need to reach node 1, but at the same time, in order to complete node 1, we first need to complete node 2, right? Like we discussed before. So because of this cycle, we are not able to come up with any valid ordering, and hence topological sort is not possible here. So you must keep this in mind. Now that we have studied topological sort, let's go back to our problem course schedule and see how this problem is related to topological sort. Now coming back to our problem, we'll be given some number of courses along with the prerequisites array. So let us consider this example where the number of courses that we are having is 4, and this is the prerequisites array, which comprises of pairs of vertices. Using this prerequisites array, we will build our graph. So if we are having a pair 0 comma 1, then it means that in order to complete course 0, we need to first complete course 1. Course 0 is dependent on course 1, okay, which means there should be a directed edge from node 1 towards node 0. If I show you the graph, it would look something like this. So in this graph, we have a directed edge from node 1 to node 0, which means that course 0 is dependent on course 1. Similarly, we have a directed edge from course 2 towards course 1. It means that course 1 is dependent on course 2, and same way course 1 is also dependent on course 3. That's why we have a directed edge from node 3 towards node 1. Okay, we need to determine whether we can perform all the courses or not. Now the first thing that we must understand is that we should always begin with a course that is not dependent on any other course, right? So what we are going to do is, for each vertex which represents a course, we are going to find the integrity of that vertex. Integrity means number of edges directed towards a particular node is the integrity of that node. To calculate this integrity of all the nodes, we are going to take an array of length n. So let us call this array as integrity, and we have 4 courses, so the length will also be equals to 4. Okay, to calculate the integrity, all we need to do is we need to iterate through this prerequisites array. As we have already discussed, that if we are having a pair 0 comma 1, means that we have a directed edge from course 1 towards course 0, right? Because of this, the integrity of course 0 should be incremented, and in the problem statement it was also mentioned that all the courses are labeled from 0 to n minus 1. So here we are going to increment the integrity of course 0. Similarly, coming to the next pair, is that course 1 is dependent on course 3, and it means we have a directed edge from course 3 towards course 1. So we are going to increment the integrity of course 1. The next pair that we have is 1 comma 2. So course 1 is dependent on course 2. We have a directed edge from course 2 towards course 1. In degree of course 1 will again be incremented. So the in degree of course 1 will become 2. Our in degree array will be ready, where each element is the in degree of the ith vertex. Along with this, we also have to prepare the adjacency list. So let us quickly make that. So in our graph, from node 0, we don't have any outgoing edge, which means from node 0 we cannot reach any other vertex. Hence, node 0 will not have anything. Coming to node 1, from node 1 we have one directed edge towards node 0. It means that from node 1 we can reach node 0, and that's all. Then coming to node 2, from node 2 we have a directed edge towards node 1. Corresponding to node 2 we will have one neighbor, which is node 1. Then coming to node 3, we again have a directed edge from node 3 towards node 1. It means that node 1 is a neighbor of node 3. Okay. After this, we are going to implement a BFS algorithm. We'll be taking a queue. This is our first in first out queue. Now in this queue, in the beginning we are going to push only those vertices whose in degree is 0. Why? Because it means that those vertices are not dependent on any other vertex. We can begin with those courses. Okay, so for that we will iterate through our in degree array. As you can see that course 2 and course 3 are having their in degree 0, so we are going to push them in our queue. Now after pushing the courses with in degree 0 in our queue, we are going to begin our BFS algorithm. One by one, we will pop the vertices from our queue each time. Firstly, we are having two vertices 2, 3, so we will pop them out one by one. So first vertex is 2. After popping it, we are going to iterate through the neighbors of this vertex. Since course 2 is only having one neighbor, which is course 1, so it means that now we have performed course 2, the in degree of all the neighbors of course 2 will be reduced by 1. The in degree or the dependency of course 1 is reduced by 1. Okay, I hope it makes sense. So it will become 1 now. And then we are going to check if the in degree becomes 0, we are going to push that course in our queue. But since the in degree is not 0, we are going to continue. Now we will pop the next course from our queue. So now we have course 3. Again we will iterate through the neighbors of course 3. So course 3 is again having only one neighbor, which is course 1 again. So it means that now we have completed course 3. In degree of the neighbors of course 3 should be reduced by 1, right? So we are going to reduce the in degree of course 1. Since the in degree of course 1 has become 0, it means that now this course is not dependent on any other course. That's why we are going to push it in our queue. Now in the next turn, again one by one we are going to pop all the courses that are present in our queue. So there is only one course present, so we will pop it out from our queue. Now this time we are having course 1, so we will iterate through all the neighbors of course 1. So course 1 is only having one neighbor, that is course 0. So it means that course 0 was dependent on course 1, but as course 1 is completed, which means we should reduce the in degree of course 0. So the in degree of course 0 will be reduced. Again we will check if the in degree becomes 0, it means that this course is now not dependent on any other course. The courses on which this course was dependent are now completed, so this course is also good to go, so we will add this in our queue. Now lastly, again we will pop the course out from our queue. So we are having course 0 in our queue, so we will pop it out. Again we will check the neighbors of course 0, but in our adjacency list course 0 does not have any neighbor, any outgoing edge, because of which we are done with this course as well. Once we are done with our BFS, all we need to do is we will once again iterate through our in degree array, and if the in degree of all the courses is 0, it means that all the courses were completed and we are going to return true. If in degree of any course is not equals to 0, it means that that course we were not able to complete because there was some cycle present in our graph. In that case we are going to return false. This particular algorithm where we find the in degree of each vertex and then we perform BFS, this algorithm is also known as Kahn's algorithm, and I hope the explanation was clear. Now let us move to the coding section. So this is the code. We have first taken a dictionary for our adjacency list, and I have initialized this in degree list, uh, which will be of length equals to the number of courses given to us. Then we are iterating through the prerequisites array and we are preparing our adjacency list like we discussed, and also we are updating the in degree of the courses. After this I have taken a queue, first in first out data structure, then uh, one by one we are iterating through all the courses and we are checking if the in degree of a course is 0, it means that that course is not dependent on any other course, and hence we can begin with that course and we will uh, append that course in our queue. After that, this is our standard BFS. uh, in each turn we will determine the length of the queue, and that many times we will pop courses out from our queue. For each course we will iterate through the neighbors of that course with the help of our adjacency list, and then we are going to reduce the in degree of the neighbor because we are done with the current course, so the in degree of its neighbor should be reduced by 1, and then we will check if the in degree of neighbor becomes equal to 0, it means that that neighbor is now good to go and we will add it in our queue for the next turn. Once we are done with our BFS, once again we will iterate through n courses given to us and we will check the in degree of each course. If the in degree of a particular course is not equals to 0, it means that because of the presence of cycle in our graph we were not able to complete that course, hence we will return false. If the in degree of all the courses is 0, we will return true. Okay, so this is a pretty simple code. If you submit this, it will surely get accepted. So to summarize once again, you can go through this algorithm. Lastly, the time complexity of this algorithm is big O of v plus e, where v is the number of vertices and e is the number of edges. It is same as the time complexity of BFS. So I hope the explanation was clear. If you are new to this channel, please consider subscribing it and also share it with your friends and juniors.